This year in pre-calculus, we're going to spend the entire year talking about functions. So it's probably pretty important before we do that we go through and do a quick review of functions, material that we should have learned in Algebra 1, but that's going to be essential background information for where we're going to go. So in order to explain functions, if I show them mathematically, I could give this idea of comparison. Something like y equals mx plus b would be a function, and something like x squared plus y squared plus 2 equals 12 wouldn't be a function. But if you're standing there looking at it, you probably know that that's slope-intercept form, and it's something normal, so maybe a function is something normal. But then you start looking at this, and you're like, okay, there's squares everywhere, but what's the difference? So let's take a step back, and let's look at a non-mathematical example to explain the difference between a function and a non-function. So if I look at an example, the best one I can come up with is the difference between a parking meter and a slot machine. So a parking meter, let's say you put 25 cents in. When I put 25 cents in, let's say I get 1 hour. Now if I put another 25 cents in and think about the additional time I'm going to get another hour. I put another 25 cents in, I'm going to get another hour. No matter how many times I put 25 cents in, I'm going to get 1 hour out of my parking meter. It's very predictable. I don't know what I'm doing for 4 hours, but it's very predictable. But if you think about a slot machine on the other hand, let's say I put 25 cents in, and maybe the first time I get nothing. And I like putting slot machine quarters in, so I put another quarter in. This time I get, $1. So I'm still ahead. Maybe I put another 25 cents in, and I get nothing again. And lastly, I put 25 cents in, and I strike it big. I get $5. So look at the difference. Over here on the left, with my parking meter, I have consistency. It's consistent. But over here, in my non-function, I don't. So it's not consistent. I can predict what's going to happen with a parking meter, but I can't with a slot machine. And that's the same thing that happens with a function versus a non-function. I can predict what's going to happen with a function, but I can't with a non-function. So let's do 3 quick definitions. 3 definitions that'll set the stage for what we're going to do this year. First one is the definition of a function itself. And I'm going to say that a function is a set of rules that takes input. So it's going to take input and change it into, I'm going to leave it blank, and then output. So a function is a set of rules that takes input and changes it into output. But there's a word missing. If you look back here for a second, both of my parking meter and my slot machine take input and make it output. Input and output. They both do that. The only difference is with the parking meter, it's consistent. So that's going to be my key word here, is consistent. It's consistent output. So input leads to consistent output. That's what a function does. Now when we go talking about functions, there's 2 more definitions I need. I need the domain. When I talk about a function, I can talk about the function's domain. And the domain is the set of all input values. And that's everything I can put into the function. Usually it's going to be my x's, but not always. It just depends on how the function's set up. And with domain, we normally think about the term range. So if domain is input, it makes sense that the range is the set of all output values. And that's usually my y's. So input values is the domain, output is the range. So these are three really important terms that we're going to work with the entire year. So going back to some ways in Algebra 1 that we represent functions. And the first way is what we call a mapping diagram. So mapping diagram. It's important that we understand how to read these. That way we can understand what a function does. Every mapping diagram has two columns. It has the input and the output. So let's say that we have a function that takes in even numbers, 2, 4, 6, 8. And then the function gives me back odd numbers. Let's say 1, 3, 5, 7. And then a mapping diagram is going to show you how this works. So an input of 2 leads to 5. When I put 2 in, I get 5 out. 4 gives me 3. Say 6 gives me 1. And 8 gives me 7. So that's a mapping diagram. And I kind of already said that it's a function, but let's look at why it's a function. Remember, functions are consistent. So if I look at the 2, 2 goes to 5 and nothing else. Every time you start at 2, you end up at 5. Every time you start at 3, you end up at 4. Every time you start at 6, you end up at 1. And every time you start at 8, you end up at 7. It's consistent. So this is a function. And like we said on the last slide, for a function, we can always give the domain and the range. So the domain is all the input values, in this case 2, 4, 6, and 8. Notice how I just list them out. The output is 1, 3, 5, and 7. So there's my function with its domain and its range. Let's suppose I have a second example. So if that's example 1, example 2. Example 2 might look like this. Let's say that the input column is 1, 2, 3, 4. And the output column in this case is going to be letters A, B, C, D. So this possible function takes numbers and changes them into letters. And it does it in the following way. 1 goes to A, 2 is going to B and C, 3 goes to D, and 4 goes to A. So I need to determine, does this represent a function? Is it consistent? So if I take 1, he goes to A, and he always goes to A. If I take 2, he goes to B, or he goes to C. He's not consistent. I don't know what 2 is going to become. I'm okay with 3 and 4, but it's 2 where I have my problem. This is what makes my mapping diagram not a function. The input doesn't go to consistent output. 2 becomes B sometimes and becomes C other times. So here are mapping diagrams. Another way that I can represent functions is I can represent them as a set of ordered pairs. Now, when I represent them as a set of ordered pairs, honestly, I think the most difficult part of this is drawing the little curly brace. And then I list out my ordered pairs. Let's say 1, 3, let's say 2, 6, -4, 3, and 6, 1. Now, functions are all about input, output. So let's figure out what's what here. If you remember, every ordered pair goes x, y. So really what this is saying is my input of 1 becomes an output of 3. My input of 2 becomes an output of 6. -4 becomes 3. And 6 becomes 1. So I look at it and say, okay, am I consistent? Does 1 always go to 3? Yes. And he goes to no one else. 2 always goes to 6 and no one else. -4 always goes to 3 and no one else. Notice it's okay that they both go to 3 because -4 still only goes to one value and 1 only goes to one value. And 6 only goes to 1 and nothing else. So this is a function. And when I list out my domain and my range, I like to put them in numerical order if I can. So the domain is going to be -4 and then 1, 2, and 6. And the range is going to be 1, 3, and 6. Notice how I don't list the 3 twice, even though it's in 2 different parts of my function. If I have another example really quickly, I have something like 2 comma 6, 2 comma 4, and 2 comma 12 as my possible function. Remember, this means 2 becomes 6, 2 becomes 4, and 2 becomes 12. This is kind of just the exact opposite of a function. 2 is becoming 3 different things. I don't know the consistency there. So this is obviously going to be not a function. And when I say that, I like to say something like 2 goes to 6 and 2 goes to 4. That's all I need to show that's not a function. I don't need the last one in there. So those are sets of ordered pairs, a second way to look at functions. And one last way to look at functions is I can look at them as a chart. It's really just another way of doing ordered pairs. So usually we look at x, y's, and I can give my values along here. So let's say that I have 2, 1, 3, 1, 6, 1, and 8, 1. And just like the ordered pairs, this is showing me input up there and output down there. So it's saying 2 becomes 1, 3 becomes 1, 6 becomes 1, and 8 becomes 1. And you might get a little nervous about this because there's a lot of 1s, but it doesn't matter. 2 only goes to 1 value, 3 only goes to 1 value, 6 only goes to 1 value, and 8 only goes to 1 value. It's a boring function, but it is a function. It's consistent input that goes to consistent output. So domain and range, the domain is 2, 3, 6, and 8. The range is just the number 1. I'm not going to do a second example for a chart because it works exactly the same as ordered pairs. So now what you need to do is look back over the sheet that I've given you, the first page of that packet, and try to determine how much you remember about functions. Try them out, watch some other parts of the video if you need to again, and come in with that filled out and ready to go.